Hi, geochemists. I'm hoping that this is recording both the image on my screen as well as my voice. I have been successful at accessing the sandstone petrology tutorial petrographic image atlas. I want to give big thanks to Austin Abels and to Tim Parker, who made it possible for me to move the tutorial from the server at Whitman, where I had made this available for our class actually a couple of years ago, but now none of us have access to the server. And then Tim Parker is letting me use his PC and explain to me how the video program Snagit 2020 works. In addition to those credits, I want to be sure and point out who created this tutorial. Kitty Milliken was the professor at University of Texas, Austin. Sukju Cho was a postdoc associated with her, and whose primary project, I forget if Sukjo was a PhD student or a postdoc, but this represents many years of work with Kitty Milliken's team. So it really is worth considering purchasing this tutorial for yourself. It is available on the American Association of Petroleum Geologists website for something like $20. And just to point out, for copyright purposes, I have already purchased, I think, 10 to 12 of these tutorials on DVD, so I have enough for everyone in our class. So I believe that we are in copyright copyright obedience, I guess I'd say. Okay, this is clearly off the cuff. All right, so I'm going back to the main page here, and again, my motivation for doing this is that we're about to enter talking about mineral reactions, chemical reactions. So we're going to practice inferring what chemical reactions have happened in the past. We're going to attempt to write a balanced reaction. We're going to be thinking about acids, bases, hydrolysis, and how to work with solubility constants. Again, there are computer programs that allow us to calculate solubilities like freq-C. So we will spend less time on those kinds of equations and more time looking at graphical summaries of multiple solutions of solubility equations. But first, I especially find that those sorts of concepts and calculations mean more to me if I can tie that to something in the real world. So that's what we're doing right now. All right, if you do not remember the difference between a quartz arenite, a litharenite, and an arkose, I encourage you to look that up, because these are some fundamental concepts that you could be asked about on your oral exams, for example. And you are welcome, once we get back together, you are welcome to borrow these DVDs from me anytime. And so you can do this tutorial to review sandstones, compaction, texture, etc. What we are going to do right now is we are going to investigate arkoses. And with regards to arkoses, we can be thinking about provenance. Where is the material for the arkose coming from, and how does the arkose itself give us the clues to deduce its history? Instead, with aqueous geochemistry, we're really thinking about diagenesis. All right, so if I have been successful in my movie making, the next thing that you are going to see is that I will have inserted a page that will list numerous terms that I want you to take notes on. And this may or may not be review from another class at Whitman, but these are really important terms if you're interested in hydrogeology, if you're interested in carbon sequestration, if you're interested in oil and gas. These are just really basic terms to understanding sedimentary rocks. So take a look at those terms, get out a paper and pencil or however you want to take your notes. And what we will first do is we're going to go into the goals page and you will be seeing those terms highlighted. I'm going to try not to read word for word all of the text on the goals page, but that page is going to introduce us to terms as well as prepare our minds to understand why we are looking into these images. And then after we look at the goals page, I'll bring us into these tutorials, and it may in fact be most sensible for me to record. There are 3 tutorials that each have between 12 and 17 images, and so it may be more sensible for me to create a separate video clip for each tutorial, just so that you can manage your time and take this in small chunks. And again, normally you would have been doing this exploration on your own, and then later, after we learn all of this stuff, I will be uploading a separate homework assignment where you are asked to figure out the balanced chemical reaction, where you're asked to maybe do 1 or 2 solubility calculations, and then really you're going to be using these graphical images that summarize solubility conditions. You'll be using those to think about what's happened to these rocks. Okay, so we're going to go into the goals page now. All right, we're looking at Arkose diagenesis, and my goal here is to give you time to read this page, and I will periodically click on each of these terms. So let's make sure we all know diagenesis. Clearly, you all learned the term weathering in introductory geology, and that term was repeated throughout various classes, especially Lyman's geomorphology class, and if you took Nick's classes on soils or hydrogeology. But let's make sure we understand what the authors of this tutorial mean by weathering, because it's a little more specific. Okay, so I really appreciate that what you and I are going to be looking at happens after disaggregation and deposition of all these detrital grains, and we're going to be thinking about dissolution of unstable minerals due to groundwater passing through here. And then we're going to be thinking about the precipitation of new mineral phases, which might be clay minerals, but on the other hand, it could in fact be the cement for the sandstone that is being precipitated. Oh, okay, so sorry, I am not a PC person here. I'm not used to PC buttons. So notice in this paragraph, we're going to be looking at images of thin sections of the rock. And so this tutorial mimics what we could do if we had the thin section and the petrographic microscope. I know that at least 2 of you have never done this before. Don't worry, because the tutorial actually provides all of the information that you would be learning. So don't worry, this is meant to mimic a microscopic exploration of these rocks. So notice that feldspars are an important constituent of arkose rocks, and they're going to be highly prone to alteration by our groundwater. Let's take a look at this term vacuoleization. So think of this as the groundwater is interacting with the feldspars and it's dissolving the feldspar, but at the same time the precipitation of new material and the dissolution of the older material means that you can trap little bits of the water or gases into the mineral that's actually being affected by the aqueous geochemical reactions. Okay, lots of terms here. I might make this its own video clip. Okay, detrital, I hope you know detrital, but let's check. Now I might be going through this too rapidly. You might read more slowly, or you might want to read it more than once. But of course, then my hope is that you can pause the video and or repeat the video and get all the information you want. Macroscopic hopefully makes sense to you. It's something with the visible eye. But let's take a look at secondary pores. We're going to see that authigenic comes up as a term in the next paragraph, but I don't believe that cement is repeated very often in this goals page. So let's make sure we're all clear on what a cement is. Okay. Now, you might be thinking, when's she getting to authigenic? I want to point you down to this sentence. Patchy areas of replacement by authigenic minerals are also characteristic of the detrital feldspars. So let's take a look. So we're talking about replacement by authigenic minerals. Okay, so we're getting the sense that the authigenic mineral will be the mineral that is newly stable. It is the mineral that is stable in the new pressure, temperature, and aqueous geochemistry conditions. And replacement occurs as a detrital grain from that original sedimentary deposit. That grain will dissolve, and as it dissolves, or after it completely dissolves, the new mineral, authigenic mineral, is going to precipitate in there. Now notice, cements are also new minerals. They were not there when the sediment was originally deposited. But the difference is that that primary pore space, which is the pore space within that sediment that's left after compaction, cements go into the primary pore space, whereas authigenic minerals go into where the specific grains were before. So here's our primary porosity definition. Okay, so a cement fills a primary porosity. Replacement is the new authigenic minerals. So here's our authigenic definition. Okay. Now, sometimes we need to see where that pore space is. How do we know whether it's primary or secondary porosity? That will be made clear by the images that we see. However, just seeing where that pore space is means that we're going to use a material, a dye, in a dyed epoxy that is going to help us see that. So I'm sorry about my youngest son stomping around upstairs. I hope you can't hear that. Okay, so here's what we're going to do. We're going to do a colored epoxy that will make the pore spaces visible. And in all of these, the epoxy that they have shown is a blue epoxy. So when you see things that are blue, that is where the pore space is. I think intragranular is clear. I think I showed you secondary porosity already, so I'm going to skip that. Okay, now we're starting to find out what authigenic minerals we might expect to see. And notice that they're starting to talk about clay minerals. Cerussite, a phyllosilicate, whose composition is between illite, which is more iron and magnesium rich, and muscovite, which is a pretty pure potassium aluminum micaceous phyllosilicate. So cerussite is in that middle solid solution area or spectrum of compositions. Okay, notice that we can grow a new feldspar. It's actually possible to take a more calcic feldspar, dissolve the calcium, and use the remaining temporarily dissolved ingredients to grow albite. Okay, so we can have albitized feldspars, but we'll be able to tell that they're new to that rock because we'll see the vacuoles. We can also have authigenic carbonates, and this is going to be a key idea when we're thinking about carbon sequestration. Now, it's true that carbon sequestration is currently being done by pumping fluidized CO2 into old sandstone reservoirs from which hydrocarbons have been taken out. Okay, so we have some underground reservoir of oil or gas, especially oil, and the oil has been pumped out. However, that process leaves a lot of oil behind. So a lot of oil companies have begun pumping CO2 into sandstones. And you can have development of carbonates into the pore space. However, the thought is that normally that fluidized CO2 is going to stay fluid and could escape at a later date. Instead, we want to think about authigenic carbonates forming in our Kosis as a metaphor or similar process in a way to what will be happening in our basalts that have primary porosity. Think about what is creating the primary porosity in basalts. Think about the interior of a basalt flow, and then think about a basalt flow at the base and at the top. And the highest primary porosity will be in those intraflow boundaries, those contacts between one basalt flow and an overlying basalt flow. Okay, I'll give you just a moment to read this material in the last paragraph, and then I think I'm going to bring this video to an end.